Okay, so we continue from where we left last time. So, some of the definitions I will rewrite again for our convenience. X n is the data vector at the filter input at nth clock, which is x of n then the data matrix. The last row was transpose version of this, then x transpose n minus 1 dot 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 x transpose 0. We are assuming all data to be 0 before n equal to 0, which basically if you take out this part, it is x n minus 1, capital X n minus 1. All these were discussed last time. So, I will not go to explanation again. This was one thing. Okay. Then we had a lambda forgetting factor, which is, and lambda was typically 0.99 or something. So, we had this matrix lambda to the power n, lambda to the power n minus 1 dot 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 lambda square 1 0 0. So, if you take out this part, so this 1 remains, all of them have lambda, take lambda common. So, it was lambda to the power n minus 1, then it is n minus 2 and dot dot dot, it is 1. So, it is lambda to the power, the submatrix is this. If you take out lambda, it is that lambda. So, you are left with lambda to the power n minus 1, n minus 2 dot 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 up to 1. So, that is your this matrix lambda n minus 1 and then multiplied by lambda which you took out. Remaining part 0 0, there is 0 transpose because it is a row vector, there is 0 column, it is 0 vector 1, this is the 1. This we did. Then that optimal weight was this x n transpose lambda n all invertibility of this was discussed at length. When invertible, sometimes it may not be invertible, especially when we are in the early stage. There is small n early stage of the iterations, there is small n time index is less than capital N, something like that. All these were discussed, but we are assuming that for the time being small n is larger than capital N, and this is invertible. Under that we have dn. Dn is the desired response vector. So, if you take out this part, it is d n minus 1 vector and then scalar. Okay, these are the things. This is actually generalized pseudo inverse of W n. Normally, in pseudo inverse, this lambda is 1. So, lambda n matrix is identity. It is just x n transpose x n inverse, assuming it is invertible x n transpose. This part is the pseudo inverse. Now, I have brought in that additional factor, weighting matrix is called. Okay, weighting matrix, weight factor is lambda. So, it is more generalized version of the pseudo inverse, but that times d n is W n. All right, these were the definitions, and then we worked out further. This matrix, this part. Okay, let me see. This part I call A n. Let me go to the next page. So, A n was okay. This A n. Then we have seen x n transpose lambda n. Previously, we have seen this is a repetition, but still does not matter. We can do sometimes some repetition. if you take xn transpose, this first row becomes first column, second row becomes second column, like that. So, first comes xn minus 1 transpose, then it gets transpose and comes first, and this last column, last row becomes last column. So, x transpose n the row, so column will be x n. So, it was discussed. So, this is x n, and as we have done in the previous page, it was lambda times, sorry, so if you multiply this into this plus x n vector into this 0, x n column vector 0 transpose is a row vector, but that will give rise to all 0 matrix. So, it is x n minus 1 transpose matrix times this matrix. So, it was and then this matrix times 0 column vector plus x n vector times scalar 1. So, you get x n. All these were done last time in detail, it is just recap. This is one thing, then after this you have to multiply it by x n. So, x n transpose, so actually a n is means this times I am writing this means this above thing into x n, and x n you have seen x n minus 1 okay. And so, that by virtue of that block matrix multiplication rule, this block will multiply x n minus 1. So, it will be transpose x n minus 1 plus x n x transpose n. This is a very important result. This is equal to a n minus 1. Same n, if you replace n by n minus 1, you get this. So, a n minus 1 plus this. There is a lambda factor I missed out here, x n, yes, lambda into x n minus 1 transpose this. So, is lambda, so this lambda is here. This is a very important result. This shows how from a n minus 1 a n is generated. It is multiplied by lambda. Lambda is less than 1. So, every element here is suppressed by a small factor, by a factor which is almost 1, and an additional matrix column vector into row vector, additional matrix is added. That is how from n minus 1 instance we move to nth instance in terms of for the A matrix. A is this. So, this is an important result. Then using matrix inversion lemma and always assuming invertibility, we obtain this very important result, lambda inverse. So, from the inverse also, from corresponding to n minus 1th index, how the inverse of A at the nth index is generated, that also you can work out using that matrix inversion lemma, and that was actually this by there is a scalar, this scalar lambda inverse x n transpose a n inverse x n, row vector matrix column vector, matrix into column vector is column, row into column is scalar. So, this whole thing is a scalar, this times this matrix part. Okay, let me draw a line here, so that This is not mixed up with that. All right. This we obtained. Then I defined a vector, gain vector Gn is A n inverse Xn, and this turned out to be this. We worked out, I am not going to re-derive things, I am just quoting the result. It was lambda inverse, this first two, sorry, denominator as it is, there is a scalar that does not change. This is n minus 1. Lambda inverse by this denominator and these first two terms. That was Gn is a gain vector. See one thing, computing the inverse of a matrix is very cumbersome and all, but here we do not compute the inverse explicitly. If the inverse is given for the previous clock, so this is given. So, just by this given matrix in all these places, you work out the sum this and you get new inverse. So, you do not have to calculate the inverse of A n explicitly, requiring a lot of computation. From A n minus 1 inverse, you generate A n inverse just by the equation like this, where this A n minus 1 inverse is known. So, this is known, this is known, this is known, this is known. Okay. So, this was G n. Using this G n, we also had obtained this relation. A n inverse can be written like this, first term as it is, minus take 1 lambda inverse, the remaining part is G n, this part is G n, and then last two. All right, and take lambda inverse common, A n minus 1 inverse common for both sides. So, that means I have to have an identity matrix. Matrix identity into this is this minus just G n times x transpose n, that is all. All right, this is common. So, these are the relations we derived last time, and now I have to consider this W n, I have to work out W n using them, A n inverse, okay, and this relation. So, now W n is A n inverse and remaining part was x n transpose lambda n d n, right. Now, A n inverse, this we have seen x n transpose lambda n, x n transpose lambda n is this lambda x n minus 1 transpose lambda n minus 1 and then x n. And d n. Now, A n inverse x n, that was defined to be G n. A n inverse x n is G n. Straight away second term is G n. Second term is G n. So, first is this A n inverse this quantity lambda and straight second is G n, and also d n vector can be written as d n minus 1 vector and scalar d n. Remember this is what. So far so good. Now, A n inverse. A n inverse, we worked out lambda inverse, then this into A n n. Okay. So, we put that here, lambda inverse, then within bracket identity minus G n x transpose n and this. So, A n inverse, sorry, this is lambda inverse. Let us see again, lambda inverse I minus G n x transpose n. So, I minus G n x transpose n times A n minus 1 inverse. This much is this, A n inverse is this much. Then you have got this lambda this goes there and this G n fellow is here multiplied by this. It looks bit complicated, but actually it will be simplified very soon. First you see lambda is a scalar. So, scalar number can be brought in the front and lambda inverse cancels, so lambda goes. All right. So, you are left with I minus G n x transpose n. This is a matrix, identity matrix minus column vector into row vector, which is a matrix, times this much. This much and G n into this. Okay. Now, this is a matrix, this is a matrix, matrix into matrix is a matrix. So, this matrix and this is a column vector. So, this matrix times d n minus 1 plus g n into d n. Okay, that means I minus into this matrix times d n minus 1. So, I can put this much plus g n d n, g n into, there is a column vector, that into scalar d n. We have already seen how to multiply block matrices. So, this is one block, this is one block. So, this column vector, which is also a matrix, is divided into two block, one block another, which is scalar. So, g n times d n and this times this. Okay. Now, remember one thing, what is this? This is, if this is W n, what is W n minus 1? If you are at the n minus 1th clock, everything will become just function of n minus 1. And now, see, this is what I have here, A n minus 1 inverse, x n minus 1 transpose, lambda n minus 1, d n minus 1. So, this is nothing but W n minus 1. So, this is, let me write using different ink, I minus g n times W n minus 1 plus g n d n. d n is a scalar, d n is a vector. This is a matrix, matrix into column vector. Now, this g n, so I into W n minus 1, I is an identity matrix, that into W n minus 1 is W n minus 1. And then g n you take common, So, you have dn here, scalar dn vector, the scalar dn minus dn, if you take common, x transpose n, this is a column, gn was a column vector, x transpose is a row vector, w n minus 1 is a column vector. So, this row vector into column vector is a scalar, gn into that scalar. So, if you take gn out, it will be this. All right. I move to the next page, deliberately did it here so that you can see things and then understand how this is coming. All right. So, if I move to the next page, I will rewrite this expression again. So, W n is now obtained from W n minus 1. So, this is an update relation, adaptation now from n minus 1th clock, when you have got the filter weight vector, how to go to filter weight vector for the nth clock. So, it is an update relation. So, W n is W n minus 1 plus G n times I am simply rewriting from there d n minus x transpose n W n minus 1. Now, see one thing, suppose I use the filter, I am having x n vector, I am at the nth clock, but still at the nth clock, if I do not use W n, still use W n minus 1. So, filter output will be or equivalently x transpose n. That means, though I am standing at nth clock, suppose I am not using W n, I am using the previous cycle, I mean the W I obtained till the previous cycle, that one I am using in the current cycle suppose, and filtering the current input vector x n. So, output will be this. All right. This output is not strictly the y n was y n, when we normally see y n is W transpose n x n. All right. That is actually, if you have W n, use it to filter the current. At the nth clock you have W n, so fine, you use it to filter the input vector. So, this is output that you can do after you calculate the W n. Okay, I am changing the notation. So, let me call it W n transpose, because n is in the subscript here. So, if I find out W n, then I can happily do this filtering using a current cycle filter coefficient vector W n transpose times x n. This is what I will be interested. But for this calculation only, this calculation, that is how to obtain W n from W n minus 1, this is the update relation. I have to do this also, that is I have to put the previous cycle the weight vector, filter coefficient vector W n minus 1, that is the one I obtained by doing least squares minimization up to n minus 1th clock, taking data up to n minus 1th clock, that was W n minus 1. That if I use at the nth clock and filter the current input vector, that is obviously not y n, but just for calculation I need it. So, that is again W n minus 1 transpose x n or equal to x n transpose W n minus 1, because if you have two column vectors, say A and B, then A transpose B and B transpose A, they are same. So, it is like this. So, I cannot call it y n. So, let me call it y n minus y n minus 1 n, that is taking data up to n minus 1 and that corresponding filter weight vector. If I filter the corresponding the input at the nth clock, so that is why the n comes here. So, I am in the nth clock, but using filter weight vector that was obtained by using data up to n minus 1th clock, that is by least squares minimization taking data up to n minus 1th clock. This is not actual y n I am interested, but it is just this calculation. and dn minus that. So, this is your this y, and then if I subtract, it is not En. En actually is, we know, dn minus actual yn, but here it is dn minus this quantity, where it is n, but index n minus 1. Okay, so, I call it, and it is called a priori error. So, this is my weight update relation. Alright, this is the weight update relation, where I know how to find out En minus 1. Okay, by this Gn, how to calculate Gn we know. Gn carries the information about lambda and all. This apparently is free of lambda, but Gn carries the information about lambda. All right. So, using all this, we will write this RLS procedure as an algorithm. Oh. So, that we will work out in the next class. Firstly, we have to take care of the invariability. I am assuming that the inverses exist. I am assuming these inverses exist, but that is not only at nth clock. I am assuming a n is invariable, a n inverse exists, but I am also assuming a n minus 1 inverse also exists, like this. But this way, if I go back, when small n becomes less than capital N, we have seen earlier, then it is not invariable. The matrix capital X n for those lower values of n will be rank deficient. So, inverse will not exist. So, how to take care of all these when small n is that small, less than capital N, that is in the very early stages of the iteration, n equal to 0, n equal to small n equal to 0, small n equal to 1, 2, 3 dot dot dot, because that time it will not be invariable as such. So, how to take care of that? That is one crucial issue that you have to take care. Then just some manipulations and all, we will write all these steps in a tabular form, and that will be our RLS algorithm, which we will do in the next class. Thank you very much.